will be kind of a summary of everything. Got it. Yeah, there we go. Got it. Okay. So yeah, so this week we're going to talk about like high level machine learning, AI, all that kind of stuff, just very broad strokes, nothing too technical. Next week we're probably going to talk about data visualization and, you know, do's and don'ts and the ways in which to approach it, how to keep things simple, kind of reiterating some messages we've had before. And then on the 7th week, what I think I'll do, the last kind of content one, will be just how to get started overall. So one of the things I mentioned a few weeks ago as a homework assignment to people was to have a think about how you would do some kind of data focused project within your organization. So I'm going to try and and obviously it is kind of trying to answer the how long is a piece of string, you know, and it really depends. It could be, you know, from one, although I did hear a very good answer to that once, where they basically figured out what is the smallest amount of string that could possibly be manufactured using modern manufacturing processes, and also what's the longest that could probably be done. So they kind of calculated that range. I'm going to try and do something similar to a certain extent. I'm going to try and make it as useful and as specific as I can without getting overly specific, but also maybe give some kind of a use case. To be honest, I haven't quite figured out how to do that just yet, because if you go too general, it just becomes useless to everyone. But at the same time, if you get too specific, it might not be, I might end up not really saying things that people just can't follow because it's just too different from where they go. So that's kind of where I'm aiming to go for the 7th one. And then the 8th one will probably just be a summary of we've done, and I'll almost throw it open to the floor as well in terms of asking questions and what people are doing and all that kind of stuff. So that's kind of the roadmap. Like I said, I'd left it fairly flexible because I knew you know, any plan probably wouldn't survive contact with the enemy. So that's kind of the plan. But again, if anyone has comments on that, please let me know. Yeah, like Damien said, please feel free to pop questions into the chat if you have any, if anything kind of comes up, or if I need to explain something or whatever. But I'm very conscious of the time, and you know, I do blather a lot, so let's just get on with it. So ML and models and data, oh my, right? And it is a bit like that. I do sometimes feel, you know, I see people and they are a bit like Dorothy running through on the yellow brick road, just terrified at their surroundings, not having a clue what's going on. But so I'm going to try and, again, demystify that to a certain extent, or at least just give like a very high level explanation. And, you know, what is machine learning? When people talk about it, what exactly do they mean beyond, you know, the obvious tautology of, well, it's when machines learn. And what does it mean? So the first thing I want to say to people who feel a bit worried about this is there's a very interesting guy called Dan Ariely, and he's basically a psychologist. He's Israeli, and he got interested in psychology. If you actually look at his face closely, you'll see he's somewhat disfigured and scarred. And the reason for that is because he got caught in a really bad fire when he was very young. And one thing he noticed was when they had the bandages, you know, he was in a lot of pain as a kid. And when he was in the bandages, the nurses kind of insisted on telling him that they needed to rip the bandages off quicker, and that was better. And he knew himself, that is nonsense. If you actually peel it off slowly, it's like a certain amount of pain over a longer period of time, as opposed to a large amount of pain in a very short period of time. And people would kind of just flat out lie to him. So he got into psychology, and he got very interested then in lying. And he's done this massive study, and he's a great documentary on it, if any are interested. Now, I'll try and find it as a link. This is nothing to do with anything, like I said, really. But it's just a fascinating study around why people lie, how they do it, when do you get social permission to lie, all these kinds of things. It's fascinating. But he had a really, really good statement. This goes back maybe about 10 years now, because it's about big data. But basically, big data back then, in like, I'm talking 2012, 2013, around the time he made this statement, was basically what we mean by machine learning. And he said that big data is like teenage sex. Everyone talks about it. Nobody really knows what they're doing. Everyone thinks everyone else is at it. So therefore, everyone pretends they're doing it. And machine learning is very similar to that. There actually did a study recently where I think it was a venture capital firm or some consultancy or someone, they did an analysis of a whole load of, I think there were startup companies, but they were like round Series C or D. So they were like established companies, still growing, but still taking in capital. And they basically did a quick synopsis of AI and machine learning that they claimed this company were claiming to do. And what it turned out was I think it was 55% of the cases, but it may have been 45. What they had was a database. They basically had a SQL or some kind of SQL database or NoSQL database or whatever it was. And that was basically what they were claiming was our ML, right? So this kind of ties into that in an awful lot of, and the reason for that, I mean, there's a lot of different reasons. One, it's part of the hype cycle, right? You've got to try and sound sexy for your investors, and everyone claims that they're doing it because, it's the cool thing to do, and no one wants to be amongst the uncool kids. But in reality, it's hard. It's actually very difficult to do properly, and it's not necessarily as useful as people would think it is. Whereas a database is pretty useful. It's useful to be, if only to just keep track of your invoices and your customers and stuff. But I want to kind of discuss before we begin a little bit of the terminology, because it can mean different things depending on who's talking. And this actually used to be, like I said, I think I'm sure I've mentioned it loads of times. I run a meetup group in Dublin Data Science, used to be called Dublin R. That was a different thing, but it was basically kind of spiritual successor of it. We would all meet up and talk about all sorts of different things. We're partially online and partially in person. If any are interested, we're on meetup.com. By all means, come along. We're going to try and go back to have talks once a month. We generally try to be fairly friendly, but one of the things that boiled down was like, what's the difference between machine learning and statistics? And, is machine learning and applied statistics the same thing? Is AI any different? Like, what's statistical learning? Aren't they all the same thing? And to a certain degree, they are the same thing. Like, they're all kind of doing the same thing. However, and I was very much in that category, and a couple of people told me I was wrong. And I've actually kind of came around to that point of view, although for actually different reasons to what they were saying. And I don't necessarily think they're the same way. And the reason why they're different is, from a mathematical point of view, they're usually doing the exact same things, but often the approach they're taking and the overall goals and just the philosophy and the mindset is often quite different, even though ultimately the computer tends to be at its core doing the same thing. So I kind of want to talk a little bit about that. And I'm going to focus mainly on machine learning today, like from a cultural point of view. And like I said, because in a lot of these cases, the reason why there's all these different names, which often makes it very confusing, is, there's a certain universality to mathematics. There's an argument, is maths invented or discovered and all that kind of stuff, because ultimately, these things are all based on principles of logic, which are somewhat universal, at least within our universe. So people, discover these things kind of independently of one another. So what has happened is that various disciplines of hard sciences and even soft sciences have kind of come up with ways to solve problems. And quite often they're the same problem with a different context and with a different interpretation, but they end up coming up with similar solutions. So quite often you end up with kind of these confusing, but how is this slightly different? And machine learning primarily comes from computer science, or before that, what was actually electrical engineering. So in an awful lot of cases, some of the biggest and best computer science breakthroughs were actually technically at the time electrical engineering departments. So the reason why I'm saying to that is very important is because that approach tends to come up with a very engineering mentality. And I don't mean that in any way as disparaging. That's, but it's important to think that way. They're thinking in terms, the thinking for machine learning in general, because it comes from this computer science background and from a kind of an engineering and process background, the data tends to be tabular, right? So this isn't particularly relevant, although we will use this table later, but typically this is the type of data you would be dealing with. So you have a table which has, each row is a data point, and they're all kind of independent of one another, like it's a separate customer or a credit card or whatever it is. And then you have columns, which are the different variables that you have about this. And this is one of the standard kind of data sets that you can get, which is basically about whether or not there's going to be a credit card default. And the reason why I'm showing you this here is just to kind of give an idea, although we will be using this to illustrate something a little bit later. So typically the data comes like this, and if it doesn't come like this normally, there's a process involved in turning it into something like this, because these are how these models and approaches work. They're all working on an assumption of a single input table that you use as your input. It also has this concept of exchangeability. Basically, there's no time series or anything in it. It tends to be, each row is completely independent of one another. What exchangeability means is that you can basically swap the ordering of your table and your output is the same. But the main thing it has is it's a very, very strong focus on prediction and predictive accuracy. It doesn't care that much about the uncertainty in the output or what inferences you're making or explaining the model. Actually, that's something they've kind of had to start to retrofit lately. It's much more about trying to make a prediction about something and trying to get that prediction as accurate as possible for some definition of accuracy, what you might care about, right? And that, that doesn't necessarily just have to be the best, closest to the average one. It could be because you might have asymmetries there. You might not care too much about underestimating a value, but you really care about overestimating a value. So therefore, you penalize overestimation more than underestimation, that kind of thing. So you kind of have these kind of a metric for quality, and then you optimize towards that. And the whole idea is to treat it almost like a software development project where you're essentially productionizing the whole thing. You don't too worry really about the discoverability of model parameters. So like how those numbers are calculated, you don't really care about. All you really care about is the output, which gives you quite a lot of power, because you don't necessarily care too much. So it allows you to compare hugely different techniques, because ultimately all those different techniques will just produce a number or some kind of range of numbers, whatever it might be. And then you compare them to one another, and you don't necessarily have to worry about, well, one is using a model, one is using like some kind of function, and the other is using a geometric approach, and something else is using completely different. And when the basic machine learning techniques are generally very, very different in terms of how we go about it, but they all have this kind of almost universal structure that they produce. Like in Python, for example, everything is built into scikit-learn, and everything has its own like the same formats for doing things. Like the actual model stuff might change, but ultimately the inputs are the same and the outputs are the same. And all you have to do is change a couple of lines of code, and then you can throw a completely different approach to producing your predictions, and it all kind of works very, very seamlessly. So like I said, that's very much part of the mentality. And a great example of that, like I'm saying, is linear models. Is that linear regression and stuff has been a part of applied statistics since the early 1900s. In fact, actually the late 1800s. It's called regression because of that whole regression to the mean fallacy, and the words kind of got mixed up. And so linear regression is an example of that. And that's, it's a staple of any kind of statistics that's done. But a lot of linear models are used in machine learning as well, but you can't actually see what the regression parameters are. You can't, it just works in a very different way. All it really does is it takes the numbers in, it fits a model, and then produces an output. And you don't get to look at it in the same way that you would if you were doing, say, like a typical applied statistics approach, which cares in many cases more about the coefficients of the model than it actually does about any predictions. So there's a very different approach to this. And typically, like I said, it's got a lot of focus on production. So, when we've built and fit our models, how do we actually produce these on a regular BAU basis? And how do we scale it all up? Can we fully automate all these machine learning pipelines? So there's a huge demand right now, as people are slowly kind of realizing all of this, for data engineers, for example, to pipeline all this data so that when it comes in an automated fashion, it gets processed in an automated way. That triggers another workflow, and kind of managing all those pipelines and those workflows, and taking a software engineering approach, which is why kind of Python is so popular in machine learning now, because an awful lot of people are coming into machine learning from computer science type backgrounds. And as a result, their way of thinking about things is to use Python. And Python is massive now in machine learning. It's pretty much, if anyone's interested in machine learning now, they need at least a passing familiarity with Python, because it is like there's just so much work being done on it right now. So the other key thing, like that, so that's in terms of an emphasis on that. And like other approaches have like different emphases, like I've talked about. But the other key thing that you'll hear people talk about when they're building models is to talk about model validation. And it's basically, anyone can you can produce a model from anything. It doesn't actually mean anything. The question is it any good? Like, can I use this for prediction? So like a very big common problem is the overfitting concept. And actually John von Neumann, who's that famous data science famous statistician and mathematician, he was involved in Bletchley Park and all that kind of stuff. Sorry, not Alan Turing. John von Neumann's the guy in America. He basically has this famous comment, which is somewhat controversial, but he's basically saying, if you give me 4 parameters, I can fit an elephant, and if you give me 5, I can make it wiggle its trunk. And what the point you're making there is, as you throw more and more models, more and more degrees of freedom into a model, if you give it more capacity to fit the data, it will fit the data that you're training it on better and better. The problem is that the generalization gets worse, because what happens is at a certain point, you stop fitting signal and you start fitting noise. And the point of matter is that the noise doesn't generalize, but the signal does. So one of the big problems you have is, like, as your model gets better and better, like fits the data better and better, it may actually produce worse predictions. And there's generally kind of a curve like this, if you can see my fingers. As you build more sophisticated models, the model does better and better, and then at some point it flips over and it starts doing worse on new data. So trying to avoid this whole concept, and you can see it here, like I'm basically using more sophisticated models, as in polynomial fit. I have a straight line, and then I've got a curved line, and now I've got a cubic, order 4, order 5, order 6, and you can see it's getting better and better to fitting the data. But when we try and predict on the red dot, the better we're fitting the data, in some ways we're actually getting worse at our prediction, right? So that's kind of what we're trying to avoid. We're trying to stick in the 1, 2, 3, or 4. But this is a very easy one to look at. In practice, it's much harder to tell at what point do we need to stop. And that's kind of where you have what's called the bias variance trade-off. So the bias is the error due to the under complexity, and the variance is due to over complexity, generalization. So, you're not, with bias, you're not fitting enough signal, and with variance, you're fitting too much noise. And, and you're trying to get to that somewhere in the middle, in that sweet spot that kind of does as well as you can do. To solve that problem, you'll often hear people talk about cross-validation. So basically, it's what you do is, it's the training test split. What you do is, how do you solve that problem? What you do is you take some data, you take a subset of it that you use to fit your models, and then you test it on the rest of the data, and that becomes your test split. And the problem with cross-validation, you do that multiple times. You make multiple training sets, and often you'll have a 3-way split. You'll have your training set, you'll have your validation data, and then you'll have your test data. And what you do is that you have your model that you fit on your training data, you validate it using cross-validation or whatever with that validation set, and that gets set internally to finally produce, to figure out where you are on that curve. And then the final model gets used on the test set to get the overall model performance. So the training validation. So again, you don't, like, at a high level, you don't need to actually worry about how this is done, but you will often talk about, when people are talking about modeling or performance accuracy or all these things, they will often mention, you will almost certainly hear cross-validation. It's kind of pretty much a standard approach now. And if you don't use cross-validation, like specifically, you're probably doing something like it, but different. But no one should just fit a model and not validate it or not test it or not create some kind of test metrics. And actually, that can often become another problem, because what typically happens with new techniques is people use very well-known data sets to do this. So quite often what happens is, even the cross-validation and the testing and all that, they tend to be optimized towards that data set, even no much how you try. So quite often what you will find is, when people are talking about breakthrough new techniques that give you much better value on, say, the US postcode handwriting set or whatever, that are these well-known data sets that are kind of essentially a table stakes for any kind of model building, you're essentially optimizing even within that data set. So quite often, once you try to use it for your real world thing, you might not find these performance increases. So that's another thing to be aware of, that, you know, just because a bunch of academic papers will tell you that these are the best models to use, and, you know, because they have this best predictive accuracy, it doesn't always necessarily generalize that way. And that's, you know, that's something that you need to be aware of. Although it's generally fairly well understood now within the modeling community that this is how you need to do it. So like, this not being done is less common than it used to be. So now we're just going to talk. So that's kind of a bit background. What I just want to talk now very, very briefly is just to give a very overall idea of what people talk about when they mention various techniques, just to give people a rough flavor for what it is. And generally the way machine learning, when they talk about machine learning techniques, you generally have two types of models or approaches. And there's supervised learning and unsupervised learning. And in supervised learning, we're typically dealing with labeled data. So we have a bunch of data that has some kind of outcome on it that we care about. So it could be like, you know, the amount of money that the customer spent, or how many policies they have with us, or whether or not they've made a claim, or how much premium they have, or, you know, all these kind of different, but it's something that you care about and you want to predict that is relative to some other. So what you're trying to do is you're using other things we know about the data to predict a value within the data. And that column is kind of like the output value and it's labeled. So we know what we're looking for, and we're trying to generalize that from our data set. Oops, sorry. So there's a couple of types of this. In general, the output, that label that we care about, is either a discrete value, like it's a category of some kind, or, you know, it's a churn or not churn, or, you know, it's a Boolean value. It's some kind, it's not continuous. Whereas when it's a continuous, i.e. it's a number, that's called regression. So sometimes we have categorization techniques, sometimes we have regression techniques, and kind of, you will hear these kind of terms get used, but that's basically what they mean. If they're talking about some kind of regression, it usually means it's a continuous output, and they have some way of producing a number. Whereas if it's categorization, it's got a discrete output. So, you know, it's one of possibly 6 types of values, or, you know, you've got 6 possible values and you're giving a weight to each one of those categories, although technically that's regression, because that's actually a continuous output. But like I said, the lines sometimes blur, because sometimes also a regression technique is then discretized to give you a categorization, which you'll often find in, like, you know, logistic regression, which is basically a number between it's supposed to output a probability, but people say once it goes over a threshold, we're saying yes, and anything below that is no, that kind of thing. So you'll see these kind of terms get thrown about a lot as well. For linear models, which is probably the workhorse of most things, almost all like workhorse machine learning techniques these days tend to use a linear model for a bunch of different reasons. First of all, they're generally fairly cheap to fit in terms of computation power. They don't take a lot to do. They often do surprisingly well, especially with a bit of feature engineering, and they're much easier to maintain and train and productionize. So that, you know, they're very popular for that. And they're, like I said, they're built on 100 years worth of like statistical knowledge that people can kind of use, even if they don't necessarily use them in the same way. But basically the idea is you're fitting a line. So if you can think of this as our data here, you know, we have a linear model, we're just fitting a straight line through that. But a very common misconception is that it needs to produce a straight line. It doesn't. The linear in linear models is a technical thing. It means it's linear in the parameters, which means it's got some nice features that you can use computationally to make it efficient. But there's no reason why we can't produce nonlinear output. And a good example of that is I've deliberately fitted a straight line with that red line there, but we could actually get it to fit a curve. So I've made that basically a quadratic output, and you can see there, you know, it gives you a much better fit for the curve. But that is still technically a linear model, even though it's not producing what you would call a linear output. So just be aware of that. Some people often make that mistake, that linear models only fit straight lines. That's not actually true. But like I said, they're generally relatively cheaply to fit from a computational point of view, and from a not a performance, but like a maintenance and overall, like they're relatively straightforward to productionize. They, you know, and generalizing, you can, it's fairly easy even to like refit them. You can kind of create this almost fully automatic loop where when new data comes in, you just refit the model and you reproduce everything. And that's a nice and kind of simple way to deal with. And that's, you know, there's a whole load of libraries that let you do that. So that's kind of linear models. The other big one is decision and regression trees. And the great thing about trees is that they're really easy to explain and people understand them. So just to give an example of that, this is the credit default table that we talked about before. And we can fit a tree to this. And the great thing about trees is, like I said, if you fit a decision tree, they are very, very easy for people to understand. You can see exactly what the algorithm is doing now. I've given a very simple example. This is what a couple of nodes on it. Typically trees have, they can have much bigger size, like, you can have, there's no limit technically. The big problem with that, they typically aren't though, for the overfitting reason. Trees have a very strong bias in them. So they tend to fit the data, and you can actually get a tree to completely fit your data if you make it big enough, where you basically you just create a tree that essentially recreates the data set. So typically what people will do from a generalization point of view is they'll stop building a tree they'll pick a height or a width or whatever. They'll come up with a default. I know a few people who use this in their professional life. They like to fit trees at 30. And when I asked him, why do you use, like, where did 30 come from? He said, well, in my experience, if I fit a tree with 30 nodes on it, it usually gives me predictive accuracy enough that I'm happy with. But more importantly, I can plot the whole thing on a single page and people can look at it and understand it. And I get buy-in for it that way. And I always thought that was a really, really nice kind of story of how that works, because I could totally see myself doing that. I rarely have to use trees in practice, but that's pretty much how, that would be a criteria I would use. Because you want something, the whole benefit of a tree is it's very explainable. So if you end up with this massive tree that's hard to follow, you're kind of losing the purpose there. But you also want enough complexity in there to actually capture enough of the knowledge that you want. And you can use this for both. This here is a categorization tree. It's producing in yes or no output, but you can actually use them produce numbers as well. And that it uses the average of the trees of the nodes or something like that. But you basically just split at each one. So you can see here, it's looking at a particular, the balance. Is the balance less than 1800? If it's yes, then it goes 98% of the time it's no, and 2% of the time it's a yes. So it's saying yes, and so on. You can just follow the logic and you build them out like that way. So that's kind of what trees are doing. But as I said, they have their issues. They're really simple to understand and they're highly explainable, but they are very prone to overfitting. That's always been the big problem with them. So a couple of techniques have gone from that. Random forest is the first one. Random forests are very much, they are kind of, random forests and linear models tend to be the two workhorse approaches. And it's a very simple, you basically you fit a bunch of trees. I won't bother getting into the detail because it's not quite as simple as just randomly building different trees, but they have a very clever way of doing that. And you do like 2000 trees, you produce a prediction from the 2000, and then you have some way of getting that back to produce a final answer. And that random forests, they were actually developed again by a computer scientist who had a kind of an intuitive understanding of statistics, but wasn't a trained statistician. And he came at it from a purely kind of computational point of view. And a guy called Leo Bremen, he came out with Stanford, I think, in the early 2000s, 1980, I think, or maybe the mid 80s. And the whole thing. So actually, I think random forest for a while was trademarked, or maybe it is technically trademarked, but everyone uses it, so they effectively lost it. I can't quite remember. Technically, it's an ensemble of regression trees or something like that, but like everyone just calls it a random forest. So you'll see that those get used a lot. And basically what they kind of accept that trees are going to be very biased. So what they do is they take a lot of them and then they average out the prediction, and that reduces the overfitting, and it works really, really well. And it's relatively fast to produce. It's not quite as fast as trees or linear models because you have a bit more work to do, but because you need to produce, like, say, 2000 of them. Typically, I think a typical random forest will have like 1000 or 2000 trees, and they produce an answer, and then they work. But they also give you, because of the maths and the way they're done, they actually give you a very good estimate of the generalization error. So they have a sense of how good their prediction is, and you kind of get that for free as part of the prediction. So that's another big benefit that random tree forests have. Now, to my knowledge, now this has probably changed in the last couple of years. I'm a little bit out of touch on the really cutting edge, but a large amount of like production machine learning models that aren't like Google and Facebook and Amazon that have spent a fortune on this, the vast majority of them will be based on linear models and random forests, because it kind of works and it's relatively simple. And it's actually on the whole cost benefit analysis, it just kind of works. And there's a lot of people that understand this stuff, so you can hire people for it. There's all, there's all those kind of things. Once you get to those two, they solve like 90% of your problems and you're kind of done. And there's libraries that will do it for you relatively, like pretty much, I don't want to say completely out of the box, because there's a lot of work in terms of figuring out what you're trying to do and how you process your data and all that kind of stuff. But in terms of the actual machine learning piece, there's essentially, it's a solved problem for the purposes of actually running the code and writing the code. You just kind of, it's somewhat off the shelf. So that's kind of, that's the main things. The other one, I won't bother getting into that. Oh, the one big thing it has, like, it's self-tuning. So a bit like linear models, it's really, really easy to kind of productionize this kind of stuff. And, it's relatively robust to changes in data. It doesn't blow up all of a sudden. It kind of handles itself quite well, which from a maintenance, and in many cases, you're probably a lot of companies are willing to give up a certain amount of performance in terms of accuracy for that ease of use. It's the whole ease of use versus performance kind of trade-off. And random forest and linear models typically do very well on that, on that scale. Another thing you will hear about, and I don't want to go into it in too much detail because it's getting a bit too technical. Another thing you will hear is boosting, though, and gradient boosting machines. So they kind of take a slightly different approach to trees. They kind of look at it the other way around. So rather than, having a very high bias with, and then smoothing out the variance, they basically go very low bias, and then they take lots of them to reduce the very low variance, and they smooth out the bias. If anyone's really interested, hang on at the end and I'll happily talk about it. There's not much point in getting into it there. But the reason I want to mention it is because boosting is very popular now, because it's probably from anecdotally, now I don't have hard numbers on this, but from talking to a lot of people and from the way things are going, an awful lot of people are very, very happy with their boosting models. They are a bit fiddlier to tune and to maintain and all that kind of stuff, but without going the whole kind of deep learning hog, which is kind of another ball of wax, boosting is really popular now. So it's starting to kind of at the cutting edge of things. An awful lot of things have kind of just switched to boosting if they're not using deep learning. They use a lot of that. A good example of this was Netflix. So Netflix started out with the whole Netflix prize, where they offered £1 million if you could improve their recommendations. And they had a bunch of techniques for doing that. They actually got rid of all those techniques and they went to a boosting method to perform. So generally most of the Amazon, or at least it used to be the case, it may have changed in the last couple of years. All of the, the recommendations you see on Netflix and Amazon, I believe, come as the output of like a production, a very big high scale boosting thing to produce the recommendations that you see, like, would you like to buy this, or maybe you'd like to watch this, that kind of thing. But like I said, I don't really want to get into too much more detail. There's also things called support vector machines. These were really, really popular about 10 years ago, until they kind of neural networks and deep learning kind of became in vogue again. They're totally different. They use a completely different approach. It's not statistical. It's not it's totally they use a purely geometric method. So what they do is they basically put everything into a big feature space. You can think of it in a two-dimensional space, and then they just divide it up into regions. They figured out ways to basically draw boundaries between things. So you can kind of think of it, if it's a straight line, like I said before, anything below 0.7 is a no, and everything above 0.7 is a yes. If you kind of move that up into multiple dimensions, they start just dividing up the space, and everything on one side is this classification, and everything on this other is this other classification. So you can kind of see it there. You kind of see, and obviously some things are on the wrong side of the boundary and all that, and that's where your model error comes in. But that's kind of what a support vector machine is done. And then you can apply fancy maths to this, so that you don't actually have to have, you can have all these specialized curves that allow for the curvature and all that kind of stuff, and allow you to get better discrimination in your numbers. But they're still reasonably popular in machine learning, but less so. But they have the big benefit of they're relatively straightforward to implement in a reasonably robust way, and they're in most of the machine learning libraries now. So one of their big benefits are they're kind of easy to use, because, like I said, all these machine learning libraries are set up that almost the prediction model doesn't really matter, and you try everything. They're usually part of that list of things that you want to try. So they're very easy to use. So and sometimes they work really, really well on problems. So therefore they would get used. But generally, like, I don't think there's as much active research on them now. And I think they've kind of, because, you know, this is the other thing that the dirty little secret in this kind of computer science and machine learning world is, we are as fad driven as any other human being is. So things get popular. And, you know, once, like, deep neural networks, and deep learning is basically a neural network, which I'm going to talk about in a minute. Neural networks were basically a joke since the mid 80s or the early 90s, when essentially they just didn't work, and people didn't, and like the guys who are now superstars like Jeff Hinton, who kind of was the lone voice in the wilderness for years and years, is now considered a god, whereas 15 years ago he was kind of a cautionary tale in academia. And that, you know, so that it's another reason why I'm a bit suspicious of new techniques and all that, because an awful lot of this stuff is very fad driven. I tend to prefer tried and trusted techniques unless I really need kind of high powered stuff. The other big thing to talk about, mainly because it's neural networks, is oh, hold on, sorry. I have a question here. I'll come back to it later if you don't mind, Christopher, at the end. So neural networks, this is kind of what neural networks are the basis of all this deep learning that everyone's talking about, and OpenAI, and, you know, all the like DeepMind and all that kind of stuff that Google spent, you know, 200 million quid to purchase a company that had no revenue, and everyone thought it was a joke, but it was actually a really good purchase for both people, because Google were actually quite behind on machine learning at that point, and now they're at the forefront. So if you don't think of it in terms of actually the value of buying the company, what they were buying was leadership in the field. And to them, 200 million quid was a very, very cheap purchase for them. And I remember at the time thinking it was crazy, but someone else explained it to me that way a couple of years later. If you think of it from, you're not thinking the way these companies were thinking, Mick, you're thinking it purely as an acquisition. And all that stuff is based on a neural network. And it was based on the brain. Supposedly, it's not really how the brain works, but it's kind of how people thought the brain worked back then when they were invented, I think, in the 1960s. And the idea is you've got some income, you've got, you know, your inputs on the left, they go through a whole load of nodes, it does a bunch of fancy maths, it produces an output, and then they've got some very, very clever and advanced techniques for actually fitting these models. Again, I'm not really going to go into it, but basically the big benefit of neural networks is they've kind of shown that they're a universal approximator. So you can kind of do almost anything with these, and it's shown that that will work logically. However, what it doesn't tell you is how much computation is required. And one of the big problems with deep learning now, and neural networks in general, is that they take an incredible amount of computation and a lot of data to fit. And actually, one of the reasons people have heard, I don't know if this is actually true, but it certainly was a massive benefit to them if it wasn't. When Google started offering like a lot of storage space for photos and all those kind of things about 10 years ago or 15 years ago, and they were offering like massive storage way beyond what anyone else was offering, and they were effectively offering it either for free or at very, very low cost. Not that a conspiracy theory, but it's believed that part of the reason for doing that was they were trying to get access to a lot of data and images and photos and stuff, so that they can use those to start training models and fit that, because they recognized very quickly, actually, these machines are very, very, very data hungry, and to get useful results out of them, we need to fill them with an incredible amount of data. And, you know, they were building on that. And that's very much the case with neural networks and deep learning and all that kind of thing. And I actually will be honest, I am not the person to talk to if people really want an in-depth discussion on deep learning, because I've never had to use it. I'm always at the other end of the scale where people are just going, what the hell am I going to do with my data? And I'm doing the visualization and just trying to explain the ideas. So, and there's been so much work has happened in it now. I'm actually got to the point now where enough of things have shook out of the trees, and there's a lot of like stable libraries out there now that I would be more than happy to use them if I thought it would work. Because the other problem that certainly happened about, say, 5 years ago when they got very popular was the bloody libraries kept changing, so your code would break, and, you know, and just the entire attitude, and suddenly they would completely change. It was a very kind of unstable area, and people were changing their mind about stuff, and this thing was great. Oh no, actually, you know, because none of this stuff is really fully understood. We don't really know why neural networks work the way we do. We just kind of know they work. And that's always scared me a bit, because in the work I've been in, you kind of need to understand why the machine is producing the answer it's machine. Like discoverability and explainability is important. And neural networks are really not designed for that kind of approach. So they're much more suited to things like, you know, entity recognition in images and all those kind of things where you do have a lot of data. But it's kind of, there's a lot of work in transfer learning and stuff now that means you don't actually need a whole load of data. You can actually, because a lot of these are pre-trained and you just kind of top up the training. So like there's definitely been a lot of work in America, for example, about triaging property claims. So, and you can actually get started with a couple of thousand photos of, someone with a tree in their front, like going through their house and stuff like that, and using that to kind of triage claims. You don't need the millions of photos anymore that you would have needed 5 or 6 years ago to do that, because you can use these kind of pre-trained models and start from there and move on. So that's definitely something that is leading to their more widespread adoption. There are also neural networks have pretty much revolutionized natural language processing, which I will get to in the final section. How am I doing for time, Grant? All right, unsupervised learning is totally different. So unsupervised learning, you have unlabeled data, and most of the problems people have these days are essentially unsupervised, because the biggest problem we have, a lot of companies have lots and lots of data, but it's not necessarily labeled in a way that they can use it. They generally have big blobs of data and they're trying to make sense of what they have. And unsupervised learning is kind of a way to do that. A very good example of it is clustering. So let's say this is, again, I've just created a completely random data set there. We could create clusters in the data. So like if we want 3 clusters, you can see the 3 different colors there. But we could also cluster it with 5 clusters or with 7, right? How do you know? You don't. There is various ways of figuring out what, again, for some definition of optimal, what the optimal count of clusters are. Typically, the way we do it is I go with something that you can keep in your head. So typically somewhere from 8 to 12 or less, if I could get away with it. But, this can be a very, very useful way of like, how many different types of customers do we have? How many different types of risk have we taken on? And all this data is unlabeled and we're just trying to figure out what they do. Just to give a real world example, that it's not hypothetical, this is some actual work that I did back in the day using census data. We did some clustering on the small area map data for Ireland this was based on 2006. We put it back on a map. We're coloring it by the different clusters. I thankfully didn't get the job of naming the different, because the other problem you've got with clusters is, we've applied a label, but we don't really know what this cluster means. You have to go back into the data and figure out, what is the computer finding that's difference between this cluster and this cluster, and then figure that out and try and, put a narrative on that. And that can be a head melt of a job. And that's another reason to keep the cluster count low as well. Because, I mean, if you create 50 clusters, you have to create 50 bloody answers for that question, because it's the first thing someone's going to ask. But we found it really, really useful, particularly because one of the guys we were working with was English and didn't really know Ireland outside of Dublin. So what he found, basically, he was like, so why is there a bunch of like wealthy small area maps in Kildare? Like, are there wealthy people in Kildare? Because, he lived in Dublin, he didn't. We're like, yeah, that's like all the horse racing guys. There's a lot of wealth in Kildare and the wealthy Kildare farmers and stuff. And to me, that was brilliant, because that was like a validation of the model. Because the other big problem with unsupervised learning is it's hard to validate your models. It's hard to say, because you've no labels, right? You've nothing to measure it against. You've no way of knowing, okay, it's produced some clusters, but are these clusters meaningful or not? How do we do this? So those kind of things were actually great to say, oh, wow, it's actually picking something up there. And we could also find, like, you could pick out like the poor areas of towns and cities. The other great thing about this in terms of getting buy-in was whenever we showed this map to anyone, the first thing everyone went was, show me where I'm from, and then have a look. And they're like, yeah, yeah. That's where, the local businessman lives. That's why that's a wealthy part of, whatever town they were from or whatever. So that was another kind of, like, people were asking about getting buy-in the last couple of weeks. That's a great, and like I said, people love, A, they love maps, but B, they love that kind of stuff. So it's, putting your completely cynical hat on, if you're ever doing that kind of thing, try and, relate it to the people who have the authority in some way so that they can personally identify with stuff. So this thing isn't purely theoretical. That's, I don't want to, I'm not just saying, oh, these are things that actually are done and can be very useful for you. There are a couple of other, like, it's not just clustering though. So there are a bunch of other unsupervised techniques. There's things like topic modeling, which I will discuss a little bit in the next section under NLP. There's also things like dimensionality reduction, which is very important, because as you have more and more dimensions, more and more variables in your data, it gets harder and harder to actually detect signal. for various mathematical reasons. So being able to reduce it down to a much smaller number of dimensions, smaller number of variables, is very useful. And again, it's a very unsupervised technique, because how many dimensions do we want to reduce it down to? All that kind of stuff. But you know, there are a whole bunch of unsupervised techniques that do that. But the key thing for all of them is they're when you don't really have any kind of meaningful labels that you care about. So therefore, you're just trying to do some kind of, you're trying to put sense of it. And the reason why that's important is most of the problems that companies have will often be unsupervised problems. It's like, we have a crap ton of, you know, free text in our claims notes, and we have no idea what to do with it. Can you, you know, that's, but we figure there's actually quite a lot of valuable insights locked in that data. Can you do something with it? That would be an unsupervised learning problem. So that brings on nicely to the last major topic I want to talk about, which is NLP, natural language processing, not neuro-linguistic programming. That's a Darren Brown thing. This is, when you hear NLP, almost, unless Darren Brown has been mentioned, they're probably talking about natural language processing. That was a mistake that a couple of people made when my wife particularly loves Darren Brown, and she got all excited when I started talking about NLP one day. But yeah, and this is kind of very much, it's become much more prevalent in the last, I want to say 2 or 3 years, but I've always got to remember COVID. So say it really started to get popular in, say, 2017, 2018, when a bunch of techniques got deep learning thrown at them, and they really started to kind of ramp things up. And also things like Google Translate are almost entirely NLP based, you know, and it was all essentially somewhat unsupervised learning. They would just, like, a lot of the models were based on just taking a whole load of data and then to a certain extent getting translations of things like the Bible in different languages and then figuring out the connections between them. But it wasn't direct. They were just kind of drawing associations that way. And they had a lot of stuff like that. Almost all of them these days now use neural networks. Not all of them do, but the vast majority of the ones that are in kind of that see use are. But they tend to now, the really powerful ones tend to be very, very large. GPT-3, which is the one Google have produced very recently, has something stupid in it, like 70 billion parameters. These models are so big now that you can't actually, they're not like, it's not a library you can download and use. Basically, they're all done by API calls, and in some cases they're not free. You have to pay per call and all that kind of stuff. But, you know, to get the really powerful NLP stuff from them, you need, you know, massive, massive computation behind them. But there are libraries that can actually do some useful stuff, and I'm about to show an example where they can be. A good example is entity extraction. So most people, one thing, because it's so US focused, they always talk about the US Declaration of Independence. And I was trying to think of an Irish equivalent, and the closest I could think of is the 1916 proclamation, which apparently we had to learn in school, but I really don't remember that. I think I hated learning stuff off, so I probably just blanked that part of my life out in like first class or whatever it was. So basically, I've just taken like the first sentence or two from that, from the 1916 proclamation, and I've just ran some entity extraction on it. And this is kind of a good example. So this just comes, you literally point the text at this and it comes this out. So it can kind of identify nouns and adjectives and punctuation and all that kind of stuff. And that sounds like, why would you want to do that? But that can be very useful when trying to derive insights, because there's a lot of things you might not care about. It's nice to be just able to very naturally, from these language models, pull out what the nouns are, or the things that I can't identify, because they could be things like car registration numbers, or, you know, code words, or some kind of serial number. That kind of thing can be very useful, and you can start using this then as to input into other models to try and train things. So that's kind of, you know, you'll see a lot of entity extraction. It's something that sounds really trivial, but it's actually really, really useful. And there's quite accessible libraries to do this these days. Another one, though, is topic modeling, which is latent Dirichlet allocation. It's like a topic modeling. So there's loads of functionality around that. But basically what you're doing is you've got a whole load of documents, and you define what your documents are, and then you assign topics to each document. So kind of just to give I found this on this guy's blog. He gave a great idea. You have a distribution over topics, which is what a document is. So a document is, you know, 20% this topic and 50% that topic and 20% this other topic. And then each topic is also a distribution over the words that appear in a document. And that can be very good. It's kind of like clustering for language. It's very useful for then pulling out different topics from different documents to try and put some sense on what different, as a way of categorizing your documents, or, seeing what's going on. So this could be used, for example, we use this kind of stuff for email, so as to try and track email internally for this kind of stuff. So, these, and the great thing about this is, I mean, it's computationally, it takes a while to run them, like depending on the size of the data. I think we ran this on something like 50,000 documents and it took a couple of minutes. And then but it doesn't necessarily scale linearly. But it can be it's a very unsupervised technique, because a bit like the clustering, you've got to figure out what those different topics mean once you look at what the various entity things are. And then another common thing is word2vec that you will hear people talk about, and it's basically, it allows you to try and treat concepts somewhat mathematically. So the idea was that if I take the word king and I subtract male and I add female, I get the word queen, right? And the idea is that it tries to kind of add a certain amount of semantic meaning to this. Similarly, Paris minus France plus the UK is kind of London, and it lets you kind of do this. Now, it doesn't necessarily always work, but sometimes it can be very useful to turn words into mathematical vectors that you can then do other techniques on. So those are kind of the ones that are, I would say, the most accessible for people who are trying out, like, because there's a lot of like freely available libraries for this kind of stuff, because most of this stuff is open source, because most of these people are kind of doing, like, it's kind of an open source culture. So you publish your GitHub and you make things available to other people. And so that's kind of, I'm very conscious we're hitting the time now. I figured that would kind of take up the full hour, but that's kind of, I appreciate this was, as I said, it's probably the most technical of all of them, but that was kind of a very kind of whistle-stop tour. If anyone's interested in anything specific, I'm happy to talk about it. Let me just check that question there. It was, would the underlying issue here be an alignment problem, or is there some other reason why? Oh, so I'm sorry, I don't know when you asked that. I presume that's about overfitting or underfitting, is it?
And the overfitting, I think, Mick, yeah.
Yeah, so no, it's actually a mathematical problem. It's not inherent to any data set or anything like. It's just well known, because you make more and more complex models, you're giving more space for the model to fit the data, which means it's fitting more. It's just fitting more and more of the data. So the training set itself gets represented better and better by the more sophisticated model. However, a lot of them are just idiosyncratic to that particular training set that you've chosen. And once you go outside that, the performance drops off, because that noise, that idiosyncratic noise, isn't in the general data set. It's only in that particular training set. So you will find it's almost universal that as you add more and more parameters to a model, the fit to the data itself that you're fitting it on always decreases or stays the same, right? It always goes down, because of that nature. However, generally at some point, your general error on your general data set starts to go up again, and that's the point at which you stop training, if that makes sense. Okay, that's pretty much time, I think. How are we doing for time, Jamie? Yeah, pretty much 13:29. Does anyone have any more questions just before I go? Didn't see anything in the chat, so.
Yeah.
Okay, well, I mean, I'm going to hold on for another couple of minutes. So if anyone does have and is typing furiously, by all means, finish it. You've got a couple of minutes to ask your question. But I hope that was helpful. I know it was quite technical. I couldn't really see a way of making it, like, it was this, to go back to that one of the virtues of simplicity, but not more so. I wanted to kind of just to give a quick flavor so that people aren't completely bamboozled by the most common terms you will hear people talk about, especially people like me. But next week, we will definitely be less technical when we start talking about, data visualization and how I approach it and how we can convey essentially like quantitative things and how to think about trying to tell the messages. And so hopefully you will find that useful next week. Thank you very much.
If anyone has any more questions, pop them in the chat there for Mick, or pipe in on mute yourself. But if no one's asking any questions, we'll call a halt to it there for this week. And as Mick said, we'll look at data visualization next week. And if there's anything crops up in the meantime, drop us, either of us, a line. And we hope to see you all next week. Thanks very much for joining.
Thank you. Bye-bye.
Thanks, guys.
I've just one question on what latent, what was it called?
latent Dirichlet allocation, LDA.
Okay.
Hold on, I'll put it back up for you. Hold on 1 sec. Or to be honest, it'll come up if you Google topic modeling in it's latent Dirichlet allocation.
Great, thank you. No, it sounds something that I might be sort of looking at.
Right.
You know?
By all means, Colm, give me a shout. I mean, it's not a magic bullet. It takes a bit of work and effort, and it doesn't work immediately. Like it's not just a question of I'll throw an LDA library at this data and suddenly I'll get answers out of it. It's kind of a tool you use as part of a process, but it's really, really good. It's become it's become less popular now, and I think that's kind of because it's not necessarily using sexy NLP techniques anymore, and it's kind of fallen out of fashion. But I think it's really useful, and you can download the libraries and just kind of set it running, which to me is actually very valuable. They're libraries that are very easy to install and run, and it just kind of works. So and you can always get more sophisticated later if you need to.
Oh, great! No, just I'm sort of getting asked the question, yeah, but what is it you want to show? And I'm like, well, the data is here and we don't really know what, we have. So, we can use it to do this. We can use it to do that, Yeah,
and people want very hard. This is why there's a word science in data science, because the whole point of it is it's somewhat research, right? You don't actually know sometimes what you're trying to do. So you kind of have to go in with an open mind. That's something I'm going to talk a lot about, not next week, but the week after, is like how to think about these things and the way to propose it. And to me, the only way to do this is to somewhat de-risk it. So put like a very fixed budget that you're willing to spend and possibly turn into nothing. Because at the worst case scenario, in my experience, you won't, as long as you do it properly, you won't waste the money, because you'll also learn why things didn't work. And in a negative result, that's really important so that you don't accidentally spend more time on it later, like flogging a dead horse.
Yeah. No, that's no.
But if
next week and that week after is definitely, something for me.
And if you like, but the downside is, this goes back to culture. If that's not something that's organizationally acceptable within your organization, then this stuff probably isn't going to work. Yeah. Because they won't be willing, you can't get a return on investment, because this stuff is research. The return on investment doesn't work on a project level. It works on the overall level over a longer period of time.
Yeah.
And it's like playing poker, right? How do you know a good poker player is a good poker player? It's not because he wins any individual hand. It's because over an 18-month period playing, 5 days a week, he's up money.
Yeah.
And that's how and it's like that because it's just a very, very, very noisy process that hides the signal very well.
Yeah. Perfect. Thank you.
No problem.
Thanks, Mick.
Bye. No problem. Bye.
Perfect. Thanks very much, everyone. We'll just end it there and let people back to their work. But we look forward to chatting to you all next week on data visualization at the same time. And if anything crops up in between, please drop us a line. Thanks very much.
Thank you.
Thanks, guys.